We have seen what is PCA and one example with PCA, that's portfolio optimization and risk management. Obviously, it looks fascinating, and there are a lot of mathematics involved, from standardization till covariance matrix and your eigenvectors and eigenvalues. Pure maths were involved in this, and finally you'll get a nice uh, uh, dimensionally reduced principal components, and your number of features will be reduced uh, with a good amount of variance, a covariance that they have. Okay, this is absolutely fine, but as a lead data scientist and as a data scientist with 8 years of experience from my career, I can give you some career advice regarding the data science, but how PCA can be used, whether we can use it or can't use it because it looks like black box. Do we, will it be allowed to use it? That's what we are going to discuss now. So just let's unravel the enigma unravel the enigma limitations of PCA and feature engineering for supervised machine learning and its impact on explainability. So PCA indeed has some limitations and considerations when used in the feature engineering phase of the supervised machine learning process. The first one is loss of interpretability. PCA transforms the original features into principal components, which are linear combinations of the original features. As a result, the interpretability of the transformed features is lost. A very, very important aspect. As a result, the interpretability of the transformed features is lost. So the principal components do not directly correspond to the original features, making it challenging to explain the contribution of each original feature to the target variable. So this lack of interpretability can make it difficult to understand underlying relationships between the features and the target variable, and this is the biggest stumbling block to use this, because when you are dealing with a customer, a client project, or maybe when you are working on the internal project, so in the both the cases you have to give the reason. You have to tell why are you using this feature for the respective target variable to your either client or to your domain expertise or to your VP or vice president, whomever you are dealing with. So that is not possible in this case. You are not sure, particularly you are not sure, because the principal component is basically a linear principal component that you see is it's nothing but a linear combinations of original features. That's why you're not sure what it is. Your principal, you don't know about your principal component exactly. So the explainability, the interpretability is very less. So this lack of interpretability can make it difficult to understand the underlying relationships between the features and the target variable. So what's next? There is a clear-cut linearity assumption. A PCA assumes that the relationships between variables are linear. If the relationships are highly nonlinear, PCA may not capture the essential information in the data and might result in suboptimal feature engineering. And you will get some features, you will get some principal components, but that may not optimal results. you'll get some suboptimal results. So that is the reason, before you do that, you have to make sure, you have to plot some scatter plots, and you have to understand the relation, whether it is highly linear or non-linear. If it is non-linear, I would say not to use PCA. Next, information loss. PCA aims to capture the most significant variance in the data, but it does so by discarding the less significant variance. This information loss can lead to a reduction in model performance, especially when the discarded variance contains a valuable information for predicting the target variable. So next is optimal component selection. Uh, Determining the optimal number of principal components to retain is a biggest challenge. Retaining too few components may not capture enough information, while retaining too many components can introduce noise and reduce the efficiency of the feature engineering process. Then we got the overall impact on model performance. While PCA can be helpful in reducing the dimensionality of the feature space and simplifying models, it may not always lead to improved model performance. In some cases, it may even lead to the decrease in model accuracy. So especially when the relationships between the features and the target variables are non-linear. So this is very important. One, a loss of interpretability, then you have to make sure which is linear or non-linear. If it is a non-linear, from my side, it's a big no. Don't use PCA. If it is pretty linear, then go for this, and it's gonna improve the model performance. Okay. So now let me come to the point initially where I began, where I have begun. Okay. So as a senior, as a lead data scientist, I always suggest something to my seniors and my data scientists or my interns, that is regarding the explainability concern. So it is essential to consider the trade-off between explainability and predictive power. As PCA, principal component analysis, as PCA reduces the original features to principal components, the direct relationship between individual features and the target variable becomes less clear. This can indeed affect the explainability of the model, and it might be challenging to understand why certain features were selected. That is the reason it is pretty challenging to convey the same to your client or to your seniors or to your domain expertise where the respective project concerned people. It's pretty difficult to convey that and communicate that and explain that. So that's where the trade-off between the explainability and the predictive power comes into the picture. Now, to put it simple, in summary, PCA can be a valuable technique. So in situations where interpretability and explainability are critical, it is generally recommended to avoid PCA. This is very important, to avoid PCA where you want to have interpretability and explainability. Because when you deal with a client, of course, it is important. The interpretability is very important and your explainability is very important. In that case, it's not a good idea to go with PCA, though the data is pretty linear. So in situations where interpretability and explainability are critical, it is generally recommended to avoid PCA or use it with caution. Instead, domain knowledge and domain specific feature engineering techniques can be employed to select and engineer features that align with the underlying relationships and domain expertise. So, this approach can lead to a more interpretable model and better insights into the feature target relationships. To put it to put it everything, and if you to put it simple, in a nutshell, PCA can be a valuable technique for dimensionality reduction and feature engineering in certain scenarios, especially when the focus is on improving computational efficiency and handling multicollinearity. However, it should be used judicially and its limitations, especially related to interpretability and information loss, should be carefully considered before applying it to the supervised machine learning process. Domain knowledge and understanding of the data can play a crucial role in making informed decisions about when to use PCA and when other feature engineering techniques might be more appropriate.